Okay, so good morning, everyone. So where we'd got to before is we'd shown that this was, so we're thinking at the moment about we're thinking about geometry of the multivariate normal. Yeah, and what we've done is we'd shown a kind of preliminary result about how to transform. So I won't go through the demonstrating this again, but let's write it out. So this was 4, 3, 1. So if X is multivariate normal, A is a constant, so X is random, A is a constant length P vector, and A is a constant P by P matrix, then the main result is if we take a Y, which is a sort of general linear transformation of that X, yeah, that will be distributed like a multivariate normal, and the mean transforms like the original vector, which is not incredibly surprising, but the covariance matrix transforms just with the sort of the big A matrix part of that transform. Okay, and the point is that there's an important result that follows pretty much straight on from that, which is if we let X be multivariate normal, yeah, and let's see the Cholesky decomposition of sigma as in, yeah, and in fact, so that means that sigma is C transpose. Now, there are other matrices that obey this as well as the Cholesky, right? But you've always got the Cholesky and it's easy to construct. So we'll talk a little bit later about other matrices that satisfy this, okay? But then from just substituting in, then you C minus 1 X minus mu is a set of kind of uncorrelated standard normals. Yeah. So you apply 3, 1 for A is mu, big A is C inverse, yeah, and Y is U. Then the mean of U is C inverse on mu minus mu, which is naught, and covariance of U is C inverse sigma C inverse transpose, yeah, which is from this equation here. So C inverse, substitute that in. C inverse C transpose C inverse transpose, okay, then this is equal to 1, yeah. So that's equal to C inverse C all transpose. So that's just that when you transpose the product, you change the order of operation, right? I think we showed that in section 1, which is itself 1 transpose, which is 1. Yeah. So so the point is that subtracting the mean and acting with the inverse square root. Yeah, if you think of the chol as a square root or any matrix of A, this is a square root. Yeah, that takes away not just the mean, right? And remember, standardization, you didn't get rid of correlations. You had a matrix. When we standardized, we ended up with a matrix that was all ones on the diagonal but had off diagonals, right? 2, -1 and 1. Here we've got no off diagonals, right? So we've taken out the correlation as well. Okay. Okay, so that was why we were interested in that result. And so that could let us define the Mahalanobis so inspired by this corollary that we just had, we're going to define the Mahalanobis transform on data. Okay. So suppose we have an n by p data matrix X. Yeah. If we act with the centering, so centering is one of those, I think we'll have to use the American spelling of center to make it look at all reasonable. Yeah. So centering matrix H from chapter 2. Yeah. Then we create a new data set Y, yeah, which is H on X. Okay, so that's taking off the mean, and this has 0 mean, since H on 1 is 0. Yeah, I should probably add that to the things that we show about. Probably add that to the things that we show about H in the problems, because that's a nice one to show. And the mean of Y is 1 over n, Y transpose on 1, which is 1 over n each X transpose on 1, which is 1 over n X transpose H transpose on 1, yeah, which is 1 over n X transpose on H of 1, which is 0. Yeah. So we showed all of these. We didn't show this one here, right? But that would be another nice thing to show. You know, go back to your problems too and have a go at that. Okay. So now, if S is the sample matrix and C is chol of S. Okay, we know we can take this chol because we proved quite early on that the sample variance covariance is itself going to be positive definite, right? So it's going to be square rootable, right? So the matrix equivalent of you can't square root a negative number without strange things happening and things going complex, right? That will the whole thing. Matrices, but it's all right because we're positive definite. Okay. So S can be written as C transpose, yeah, and we can define a new new data set, yeah. With data matrix. Okay, so that's acting. So this is acting the opposite way from in the corollary, but if you think about it, a data matrix is n by p, and p is kind of the feature space, yeah? The variance covariance matrix is p by p, it's a feature space thing. So we want the chol and the stuff to do the variance covariance to act in kind of feature space, which is going to mean acting after the data matrix, yeah? So that's why we have a transpose and it comes after, right? It's going to be, we want to be in the p by p space of features, not in the n by n, or not in the length n space of like number of observations, okay? So then note that U transpose H, U is C minus 1Y transpose H. Yep, that's just substituting in things that we've seen before, which is N by D C minus 1S. Okay, so this is us trying to calculate the covariance of the new data set, yeah? And so we're substituting our definition of U, yeah, in terms of Y. And we know that then this is the sample covariance of Y, because we know that changing mean doesn't change the covariance, right? We showed that earlier. And so there's that's a -1, C -1, yeah. And then again, we're going to substitute in, we're going to spot that the S there is equal to the C transpose, right? So this should look familiar. Yeah. So that's equal to N minus D on I and so I'm already substituting in C trans. Hang on, let me write it all there, right? So that's C minus 1 C transpose C minus 1 transpose, yeah. And then those are going to cancel to give I. Yeah, though that's going to go inside there, change the order, and it's still going to give I. So the whole thing is just going to be N minus D times I, like before, yeah. So the new data, so U has unit covariance, right? Because we're going to divide that by, yeah. So covariance, U has sample covariance equal to I, yeah. And the important point is none of this assumes multivariate normality, right? So in general, the U's might not be independent, okay? They're just going to be uncorrelated. So what I'm going to do now, if it works. So here's an example. Okay. So here's an example of how this works in practice. So remember this auto data set that we've shown a lot with EDA, yeah? 4 features are chosen. They're the 4 features we were visualizing in the pairs plot before. And the data covariance is S, which is CC transpose. And so we remove those, okay? And what you'll see here is this is the original data, right? And you'll see that because there were these multiple modes, it wasn't quite multivariate normal, but some bits were quite close. Okay, so the top bit is before the Mahalanobis transform. And then once we Mahalanobis transform, yeah, you can see that actually some of them, which were quite close to multivariate normal. So you can see here, this acceleration is quite close to multivariate normal, and so is miles per gallon. So there's a very slight deviation, but once you Mahalanobis transform it, yes, this is, well, we're going to see what it means to look multivariate normal soon, but right, you can see that these are quite circular contours, and we'll see that that's this, you know, these look like one blob, right? So later in this chapter, we'll see why that matters, but I guess because what we're supposed to know is correlation, right? So you see, if these were data sets, you'd look at these and go, actually, yes, there isn't very strong correlation anymore between these points on the data set. Yeah. And we're going to see why that is associated with circular contours later. But what you'll see here is, if you remember what we were talking about Anscombe's quartet and the Datasaurus doesn't, right, is that, yes, you've taken out the correlation. So the correlation line between this would be 0, right? But you've got these blobs, right? These are, there's non-independence here. So this looks like a moon shape here, right? Or here you've got a kind of curved shape, right? So it's like the Anscombe quartet. Yes, you can remove correlation, yeah, but that doesn't mean that you've achieved independence unless the data are very close to normal. Okay, but so this is an example of application of Mahalanobis transforming to data, right? And it's sometimes it's one of a whole type of transforms that remove. It's one of a whole load of transforms that remove correlation structure, right? Okay. So are there any questions on that? Okay. Okay, so that was the Mahalanobis transform in practice, and that's going to let us define this multivariate equivalent of like measuring things in sigma. So suppose we have X and U as in corollary 432, yeah. Then the remembering that we had lots of different kinds of length and distance, right? The Euclidean length of U sorry, this is X and U, these are multivariate normals, not data sets, sorry. Then the Euclidean length of U is this, so it's the length of U, which is U dot U to the half. Okay, so how did we define U? Well, it was C inverse X minus mu. Yeah, and so we're going to write out the dot product as a transposed times untransposed, and the whole thing is to the half, right? It's a square root to give Euclidean distance, which is, when we flip that around, yeah, we're going to get a C. We're going to get a C. Okay, so I'll write this out, then I'll just explain why it holds. Yeah. And this holds because if S equals C transpose, then S inverse, yeah, equals C. So S inverse has to obey S on S. S inverse on S equals 1. Yeah. So it has to be a set of matrices that when it acts on S, then yeah, so that has to be S on CC transpose. So there has to be, that should be then C transpose inverse on C inverse, yeah, on C transpose, yeah, because the inverse is going to act on that to give 1, and then the transpose inverse is going to act on that to give 1. Right, so we've used that result here when those two bits come together, right, to give us the sigma inverse here. Okay. So I'll just put this in as an aside, right? Again, I could set that as a problem, maybe. Okay. So we can then equation 421 to define the distance of a multivariate observation X from its expected value as then this is the delta of X, which is going to be square root of X minus the mean transpose on sigma inverse X minus the mean. Yeah. This is called the Mahalanobis distance. So of course we don't always know what sigma and the mu are for the population, right, or for the normal. So often there'll be things taken from the data set, right? But here's how it differentiates the idea of, is different from the idea of a number of sigmas out, right? Which is, suppose you have a positive correlation between points, yeah. And those points then have a mean, so they have a mean about here, right? And each of the individual variables has its own sort of measure of width. Yeah. Now, if you take a point here, x1, and a point here, x2, yeah, both of these are the same distance out in like univariate sigmas, right? But we're more, x2 is sort of further away from where the bulk of the data is, right? So x2 will have, by this equation, if you work it out, and we're going to work it out in the next bit, a much bigger Mahalanobis distance than x1, right? So their Euclidean distance is the same. Their standardized distance, if you divide everything by the individual standard deviations, is the same. But their Mahalanobis distance is different because there's a correlation between these. So you're much less surprised. X1, something here, is much more typical of the data set than something that's a similar Euclidean or standardized distance, but is away from the correlation, right? And so that's it. Right, important it's that you're, if you want to check that a child is growing okay, right? You kind of try to follow the child's all the different bits of the child on their growth curve, right? And measure the head circumference and the other things, right? And you think, oh, are they following the right trajectory for their? Okay. Okay. So so if you recall, the normal is proportional to x of minus a half. Yeah. So and if you remember comparing, so I should have called the definition of the Mahalanobis distance 433. Yeah. So comparing four and one, which is this expression here, and 433, which is definition of delta for the Mahalanobis. Yeah. We see that contours of the multivariate normal are curves of, so that's contours is defined in chapter 3, right? A contour is a curve of constant probability density. So when this probability density is constant, this quantity here is going to be constant, yeah? And this quantity is like a squared Mahalanobis distance, yeah? So if the square of something is constant, that thing is constant, yeah? So, so they're curves, or in higher dimensional things like their surfaces, right? Contours of the MVN are you know. Yeah. A constant Mahalanobis distance, yeah. So for each A bigger than naught, I guess, there's a contour delta x equals a contour. Yeah. And if we write that out, that satisfies x minus mu transpose sigma inverse x minus mu is a squared, right? And that's I'm not very good at labeling equations. They are in the notes. Okay. So what does this mean? This is a condition on x, right? This is we pick an A, yeah, and we're interested, and that imposes a condition on x. So that's what the contour is, right? So for the more general case of contours, you know, if you think there's a line here, right, in a general line here, there'll be some function of x equal to 0, right, or something like that. That sort of function on the x in the real sort of p, whatever the contour is you're trying to define, right? So there'll be some that will give you the curve. If p is 2, it will give you a curve, right? But if p is bigger than 2, it's going to give you a surface, right? At the surface. Okay, so we're going to investigate what this expression is going to mean. Sorry, is that? Okay, so now consider algorithms 1 to 10 and 1 to 14. So these are the ones for eigenvalues, yeah, and Cholesky. So sigma is a p by p positive symmetric matrix, yeah. So it needs to be for the distribution to be multivariate normal. So we can construct its eigensystem eigensystem. That's a set of lambdas and these maybe with a hat, yeah, for I and P. With all the normal eigenvectors. So that bi dot v j is delta ij, right? So dot vj, yes, delta ij. So that means that each one is length 1, and they are those vectors are right. All the vectors are at right angles to each other. Okay, and the point is that if you have a repeated eigenvector, you don't have to choose the eigenvectors to obey this, but it's going to be sort of easier for our purposes if we do, right? So right, this is a different U from the other U's, but everyone always uses U for this kind of matrix, right? So this isn't a data matrix U. But this means that U, which here is the matrix with columns equal to the eigenvectors, yeah, and we'll have P of these in general. Yes, this is a P by P matrix, is what's called orthogonal. Yeah, i.e. U inverse is equal to U transpose, right? And if you think about it, this condition here guarantees that, right? That when you think about a matrix multiplication, if you matrix multiply it by its transpose, you're going to get the product of this up with the, yeah, when you rotate it around, that's going to be producted up. So you transpose U, yeah, it's going to look like these things as rows times the other one as columns. So when you do matrix multiplication, you're picking up a load of those, and you're only going to get diagonal elements, right? So that's going to be I, right? And that's sufficient for U transpose to be the inverse of U. Okay. And so this is a standard result, right? But like I said, it's slightly inconvenient if you don't pick them orthonormal, right? Because this result then doesn't hold, but you in general you can. And yeah, the point about matrices like that is that they are length preserving. Okay. So such a matrix represents a length preserving transformation yeah. Since if y is U times X, right? So y is the transformed under U. Then I transpose Y is U X transpose U X, which is X U transpose U X, which is X transpose X, because that's equal to 1. Yeah. So it preserves the Euclidean length. Okay. So that means that the map from RP to RP induced by U is all rotations combination of rotations and reflections. Yeah. And so you'll have noticed that the things we said when you're doing the orthonormal, you still are actually left with some degrees of freedom, right? And those degrees of freedom are reflections, right? You can set each eigenvalue equal to negative itself, right? And that doesn't matter, right? So if you want to be more specific, you can try to take out the reflections, but there's no particular need to do that, right? So you can try and specify the eigenvectors, sorry, so that this transform is only with rotations and no reflections, but that isn't really terribly important, right? But that's the extra set of degrees of freedom where we just say do what you want. But by setting the eigenvectors to be orthogonal, we get an orthogonal matrix. Orthonormal, sorry, we get an orthogonal matrix composed of them. And that matrix is useful. So next, note that for intuitions, right? When note that that the eigensystem equation, which is 1, 2, 8, implies that sigma u is u on lambda, or lambda is diag on the matrix of lambda i's for I and E. Yeah. So so that's just if you think about the way that this works, sigma, you've got it acting on each of the V, you know, you've got the columns that's the V1, V2, and so on. Yeah, that's what sigma U is. So each of those produces a copy of the eigenvector, but with a lambda in front of it. Yeah, this is going to equal this with lambda 1 times the column and lambda 2 times the column. Yeah. And that can be written like this. Yeah, when you think about how a diagonal matrix works. Okay, so that's just a compact way of writing. This is just a compact way of writing the eigensystem equation if you write it out. Okay. So if we post multiply this, yeah, so this equation, we post multiply by U transpose gives sigma U transpose, that's I equals sigma equals U lambda U transpose. Yeah. And hence sigma inverse, and remember when we're looking at what you can construct an inverse, if the matrix is a product, you can construct the matrix inverse by just thinking about how that product has to act. Yeah, sigma inverse is U lambda inverse U transpose, and that is, I'm going to call that equation 44. Okay, so we haven't like stated this theorem number type thing, like we just argued this through. But so let's think about it. This is helpful because the lambda, we know how to invert a diagonal matrix. Yeah. So this lambda inverse, that's just going to be diag of 1 over lambda I and P. Yeah. And we've worked out the eigensystems. And you can look at this and just see that acting, to check why this holds, just note that U lambda minus 1 U transpose on U lambda U transpose is I. Yeah, that follows quite straightforwardly. So that is what we want from an inverse for sigma. That follows, you know, that's just straightforward. So we've got now this is then a different way of writing the this is going to be a different way for writing the sigma that appears in the Mahalanobis distance and thinking about the constant curves. So we'll get on to the main result. This is going to tell us that the curves of the multivariate normal are ellipsoidal, right? In a sense, all the information is already there to work out that they're curves of an ellipsoid, but we're going to go through that next time and exactly which curves have which interpretation. Okay, so are there any questions on what we've done today or any other part of the course? No, great. So hopefully we'll finish off this bit and then we'll look at the EDA questions on the next tutorial. What I'd also encourage you to do is if there's bits where I've gone, oh yes, try this for yourself. There's various bits where I do things in full detail. there's lots of bits in the course where I do them in less detail and go check it, right? Sometimes I put that check it in as a problem. Sometimes I just say, oh yeah, check that this holds. If there's bits where you try to check it and it's not a formal problem, but you're not sure, that's also a really good use of the tutorial. If you go, actually, could you go through in more detail this argument where you sort of jumped a little bit? Yeah. Great to see everyone on Thursday.